Hey everyone, it's Julius with Computing for Designers, back again today with another video in our Apple Maps series. Today we're talking about dynamic labels. As you'll notice, it's not late night, it's actually around just a little bit before noon. So today's name is a high noon breakdown. But without further ado, let's get into it. So if we take a look here at the iOS Apple Maps, you'll see that as you're zooming in and out, the labels for things like cities, highways, streets, points of interest, buildings, they all fade in and out pretty responsively as you're going about. But there are certain decisions that are being made that are quite interesting. So for example, here, University Park is a pretty big neighborhood. You can see the font size is slightly bigger than Highland Park. Yet when we zoom in here, Southern Methodist University kicks in and Highland Park is still visible. And so there are a lot of these kind of small decisions that are quite interesting. Another example here, if we zoom in here to a great burger place called Rodeo Goat, and we have Ferris wheels right there. There are two businesses that are right next door to each other. Yet when I zoom out, Rodeo Goat is the one that wins out. And it's pretty interesting to see how this label flips from one side to the other and interacts with the Market Center Boulevard label as well, especially as we rotate. What happens if we rotate it all the way around here? Oh, it flips to the other side, right? There's a lot of really interesting decisions here. And we'll sort of cover the basics of how something like this can be implemented. And today we're really entering down this avenue of guesswork, right? This reverse engineering based on my personal experience with mapping technology, but also software in general, and guessing at basically what the algorithm, right, what the logic is here. And so we'll explore some of those basic concepts and look at what we can learn from this. Right, so a good place to start off here today is actually looking at some more historic mapping technology. So if you're not familiar with OpenStreetMap, this is actually where a majority of mapping data comes from. I'm pretty sure Apple leverages this, Google Maps leverages this. It is an open source database of mapping information. So for example, the businesses we're just looking at, Rodeo Goat and Ferris Wheelers, funnily, Ferris is spelled incorrectly here, but Market Center Boulevard is here. One thing you'll notice is that this map is not as responsive, right? It's got fixed zoom values. And if you look at the URL bar here up here, it's kind of small, but you'll see this first number 15. That's actually expressing the zoom value. So you'll notice as I zoom out further and further and further, it decreases in number every zoom level, right? And you'll see that at 1, I can fit the world many times over, right? So it's an exponential zoom level. And what we're looking at here is pre-rendered, right? The server has generated these map images already on the server, and it's being downloaded to the computer as I zoom in and out. So you can see things are blocks, and like the gray parts are just loading it in as I'm zooming around. And so you'll see that all these decisions about what labels to show here, those are still following an algorithm, but the decisions are made already, basically pre-baked into these tiles, what they're called raster tiles, because they're rasterized into images. So you'll see that the transition here is a little bit more jarring, but at the very least, it's pretty consistent as you're scrolling around, right? There's nothing flickering in and out. And you also notice that they're pretty conservative with the font sizes, right? So generally speaking, the font sizes are not huge in difference, right? So that's pretty interesting to look at. If you look at a little bit more of a modern mapping interface, probably still using OpenStreetMap data. Actually, yeah, on the bottom right here, you can see it's actually pulling from OpenStreetMap. You can see that instead of fetching these rasterized tiles, Mapbox here actually has their own technology called vector tiles. And so in that case, they're actually saving data that is not rasterized, right? It's not flattened to the image, and they're sending that to the client, right, in a very compressed format. And then they're deciding at render time how to present all the information, right? So that means that you have a little bit more flexibility with things like this kind of smooth zooming, right? So you notice that we're not snapping anymore, and so there's more progressive fading. And so in general, the experience is a little bit smoother. It's called fractional zooming, right? Because you're allowing the zoom to go between, like, let's say 14 and 15, you can go like 14.1, which is like a fraction, right? So that's why it's called fractional zooming. And so it's pretty cool to take a look at how this mapping interface has evolved over time. But still the question remains, how does it make decisions for what streets to show, at what times, what features to show over what other features? And so to look at that, we can actually go back to OpenStreetMap and let's look at something like Market Center Boulevard, right, which is here in Dallas. And you'll see right here it has this result. If we click on it, you see all this information. So these are all the tags. And this is stuff that, again, all the mapping programs out there pull from this OpenStreetMap. And anyone contribute to this, right? It's like Wikipedia. And you'll see that it's a highway, quote unquote, and it's labeled tertiary highway. And if we look at the key, right, for highway, it has all this information about what types of things there are, right? So what we think of a highway, like, an express freeway, is actually a motorway, right? And you can look at different information, right? Next most important roads in a country system, kind of linking larger towns, secondary, things like residential. And so you'll see there's actually a type of hierarchy here, which can be very, very useful, right? So if you're deciding between two streets, right, which are next to each other, and you want to decide which one of these to show over the other for whatever reason, then you might say, hey, actually at this zoom level, we care more about primary roads, right? But you might say when you're zoom in very close, you actually care more about like residential roads, right? And so these are some interesting decisions that you can make. So if we scroll over to maybe some more residential area, you can see kind of the difference in treatment, right? Whereas Singleton Boulevard is probably like a tertiary road. These are more residential roads. And you can see kind of some of the differences in how they're rendered. And similarly for points of interest, I'm actually interested in, let's see if OpenStreetMap actually has information on businesses. I don't think that's the one we're looking at. That's in Dallas. Here. All right. Okay. Great. So it actually does have a building data too. So if you're thinking about like how does Apple and Google have all this like building data? Like, yes, they do collect their own. They do their own like analysis of like satellite data to generate better shapes. But OpenStreetMap has its own as well, which again is a community-driven operation. And you can see some pretty bare bones data here. It's a restaurant. Like, is it a building? Yes. And the cuisine, it is. You won't see stuff here like ratings, right? Obviously, OpenStreetMaps doesn't have a review system, and also like popularity, which are things that like Google and Apple both have data on based on how often someone is searching, or the reviews, like the star rating, right? They could look at Yelp, right? For example, I think Apple partners with Yelp for their reviews. And so those are other information that you can use to help decide. So we've kind of touched on this idea of like deciding between when to show and hide something, but like what is that situation, right? It's really when two things run into each other, right? So if we look at most famous cuts here, and if we rotate it at a certain point, actually it just flips to the other side, which is quite nice. But if we zoom out at a certain point, it's going to eclipse something else, right? And CVS Pharmacy wins out, right? And so we're really looking here at the collision of two or more labels. That is really the situation in which you need to decide to hide some stuff. And also at zoom levels, right? At a certain level, you really don't care about certain entity types. So for example, out here, you're looking at kind of like major features, right? Hospitals, big parks, I guess Tom Thumb, which is a gas station, and a really big hotel, right? Cool. So let's take a look at the underlying challenge here, right? It's like, how does the system like figure out when these labels are actually coming into contact with each other, and then that's the case when they need to make the decision on priority. So that's really the breakdown that we're doing today. So the main idea here is really similar to in gaming, right? It's called collision boxes, right? You have these boxes that are drawn around important entities in your software game. And you're really just using pretty basic math to compare, is one overlapping the other? And then if so, some action needs to be taken. right? And they do this every frame, right? So if you think about like more modern games where they have realistic physics simulation for like boxes that break apart or like rocks that are crumbling, there's like millions of calculations that are happening every frame of the game. And if you look at an old school game like Super Mario, the concepts are actually pretty similar, right? Except it's in 2D and, you know, at a much lower frame rate. So what is actually happening here, right? If you look at one of these boxes in whatever, you know, coordinate system that the game has, there's usually some concept of minimum, right? There are numbers that are expressed, you know, positive or negative on the x-axis, and then positive or negative on the y-axis. And so let's assume that, you know, just like in Figma and most UI, like the top left is 0, 0, or you can go negative if you want. And the bottom bottom right is increasing, right? So that's kind of the maximum side. Now, if we compare two boxes, how do we actually decide if they're intersecting or not? Just looking at the coordinates, right? Just looking at the points, right? So for each box, we have the 4 corners. That's kind of the information that we have that defines a box. So maybe the formula is something like if A's maximum, right, which is this point, like 18, 18, is greater than B's minimum of X and Y, right? 15, 15, 18, 18 is bigger than 15, so yes. So maybe this is the formula. All right, so if we scroll down here, we can look at some different situations where the formula might be a little bit different, right? So if you look at this one, you might conceptualize, oh, like if B's max X is greater than A's min X, and if B's min Y, kind of top side, is less than A's max Y, and then you kind of go through all the different way, and you see the rules become really, really, really complicated. And this is a situation where you might actually want to look at kind of the failure cases, right, which might actually make a simpler algorithm, simpler formula. And that's exactly the case with bounding boxes, right? So the simplest test is actually, instead of looking at all these different situations and all these like complicated formulas, right? This like confused me to write it and to read it. You actually want to look at, well, what are the cases that show that the boxes are definitely not overlapping, right? So there's 4 simple cases that you can test, right? Is the right side of A to the left of B's left side, right? We're looking at this side and this side, right? Is this over here? Because no matter how tall it is, or sorry, no matter what Y position is, if the X right side is less than the B's left side X, then it's never going to be colliding, right? Same thing, just flipped, right? So we're checking both shapes. And then we're doing this for the y-axis as well, right? Where if it's above, and it doesn't matter where it is on x-axis, right? If it's above, then it's definitely not overlapping. Same thing if it's below, right? So with these 4 rules, right, that's how you can really, really quickly performantly test if 2 boxes are colliding. Now, in reality, it's a lot more complicated, right? Because the maps have labels that are at an angle, and that sometimes you're not looking only at boxes. You might be looking at like a curve shape, or you might be looking at a label that's, you know, kind of a funky shape. And so you might make the decision that like, hey, we actually want like really accurate like collision label testing. And in that case, you might be ending up with a shape that like, you know, looks like this, right? And in that case, you're like, oh, how do I actually like find the collision between like 2 shapes like this? And again, that's why like modern games, right? They have to do like a lot of calculations to figure out this. Like the formula here, right, that we just determined here is way not going to handle this kind of stuff. And so this is kind of like a sidetrack, but like what systems actually do in this case when they have like really complex geometry to compare is that they will actually first draw like a pretty simple bounding box around every element, and then they'll just see if try to get rid of as many non-collisions as possible, right? So like obviously if the boxes aren't colliding here, then there's no need to go and test the inner shapes. But if they are colliding, then we need to double check. Right, now we need to double check, hey, are these actually overlapping? So their boxes are overlapping, but the actual shapes themselves are not overlapping, right? And one of the nice things about bounding boxes too is you can add some sort of padding. So for example, with labels, right, you might be looking at the collisions like this, but what if you actually wanted the collision to happen a little bit sooner, right? Because you want these labels to look, you want them to look nice, right? You don't want like a really tight situation to be happening, right? So for example, you can see that sort of that the fire rescue station, it's not like a one pixel collision, right? It actually looks like, there's, maybe like a couple pixels here that give it some padding. So in that case, you could actually just say, hey, when I'm doing a bounding box, I actually want, there to be some padding, right? And then you're just simply testing the collision boxes of the slightly larger box. And that's super easy, right? Because you're just comparing numbers. So those are some of the interesting principles behind collision boxes that are fun to consider. And kind of based off my personal experience in consulting with some folks, I'm pretty sure that's kind of how this kind of software works, right? Where this kind of interaction works, where the application is testing the collision of labels, right? So in the screen, even though we only see like 20 points of interest in labels, right? There's actually like a lot more. There's probably like 50, right? If you zoom in, you'll see like much more stuff. Actually, this probably isn't a good example. Let's go to somewhere more crowded here, right? So here in downtown, you'll see that even in this block, there's like a ton of stuff. But if you zoom in, there's like even more, right? So my guess to what it's doing is that every single one of these labels, the bounding box is calculated for that label at the current render size. And then it kind of iteratively goes down and compares every single one and makes sure that things are not colliding, right? And if things are colliding, it will give preference to the thing that it decides is the most important. And that may depend, that's the design decision, right? Is it the popularity? Is it, I don't know, the size of the building? Is it, proximity to your house? I don't know, like whatever the logic is, right? So for example, like this parking symbol, right? There's a parking lot here, but they're deciding that it's not as important to show as the actual businesses here, right? And yeah, it's doing this again every frame, every second. So if you have like a 60 hertz screen or a 120 hertz screen, it's doing this even more and more, which means that it can be a little laggy at sometimes. Yeah, and I think that's kind of the basis of this interaction, which is pretty interesting, right? So again, if we're looking at this example of this Ferris wheel and rodeo goat, it's basically kind of like as you're rotating, right? At some point, the labels clip, and then it decides, hey, rodeo goat is more popular than Ferris wheeler, so we're going to hide Ferris wheeler. But it's still there, right? It's still in the background somewhere. It's just hidden from view, right? So you have all these like hidden labels, and so as soon as this becomes not intersecting anymore, it'll show it again. So I actually have some notes to go through. And yeah, so there are some interesting considerations here when you're thinking about this prioritization, especially when it comes to performance, right? When it comes to this type of thing, like performance is kind of like the main thing that you'll run into as a designer, and you're discussing with the engineer, like how do you actually make trade-offs to make the best user experience. And so in this case, you might kind of think about, okay, like, maybe we don't want to compare everything all the time, and maybe we actually want to like do some caching, right? We want to save some of the current, state, so that as you're scrolling and panning around, we're not like recalculating everything every frame. And so you might end up in situations. I documented a few situations actually. So for example, if you go to Toyota Music Factory, and let's clean this. Let me see. Sorry, let me pull this up. So I forgot where this was. I think it's over here. Oh yeah, the pavilion, right? So you'll see here, if you look at this pink pavilion at Toyota Music Factory, we'll zoom out here, so it's gone. But if you zoom out over here, oh, it kind of flickers back in. And it's one of these interesting situations where, as a user, it's like quite jarring, right? But obviously the quick fix is just to zoom in, so it's not too bad of a deal. But in that specific zoom level, it seems that the system has decided that it's collided with, what is it colliding with? Is it the trail park, maybe? Yeah, so it's deciding that it's collecting with Birds Fort Trail Park, and it decides to flip it the other side. In this case, as soon as you pan left, sorry, let me get it back to that zoom level where it was doing that glitch. Yeah, okay. As soon as it's like, okay, I'm going to flip to the other side so it doesn't collide with Fort Trail Park. but as soon as you scroll a little bit further, it disappears again. And I think what's happening is because now that it's on the other side, as soon as you scroll to a point where the Dallas College North Lake campus is now considered, right, part of the area of labels that you're comparing, because you don't want to compare labels across the entire world, right? You only want to look at the current screen, right, and maybe some padding around it so that as you're zooming quickly around, it's not like slow. So I think what's happening is like at this point, when it shows in a little bit, right, you see the little pink music icon. At this point, the campus hasn't loaded in as yet, right? So the system, the application right now is not considering the position of that. But as soon as you scroll over, now we'll hit the point where, oh, now the campus has loaded in and the system has determined that, hey, there's no good space for this music pavilion to go anymore, so we're just going to hide it. And so that's a really interesting example where you think about like, here's some of the constraints, right? Where we want to compare stuff on a screen and maybe like extra padding around the screen, right? And we don't want to go too far. And so this is like a situation where because of that performance decision we made, right? Kind of a balancing of trade-off of like, yeah, like it's cheaper to only compare the subset of things, but you end up in this case where you have these kind of like weird kind of like results. And there are actually other examples of kind of like results that change as you're kind of zooming in and out. And I don't have an example right now, kind of off the top, but it is an interesting thing to look at. So I definitely encourage you to take a look at the application and kind of like make a guess at what different types of behaviors are happening. But yeah, to me, this is like a great exercise to build technical intuition, right? Just looking at some sort of fairly complex interaction and then making some guesses at what the rules are. And then I didn't show this here, but doing some research, right? Doing some quick research as to what could be happening. So for example, I already knew about, OpenStreetMaps stuff, but if you want to look at, like how are, roads labeled on maps, right? You could understand like, oh, like here are some articles around like road maps, or if you want to like look at like, bounding box collision, right? You can see a bunch of interesting videos and articles and Stack Overflow answers, and that's actually like where I got the equation. Not this one, but yeah, actually this first one from Mozilla, right? It's a pretty simple formula here, right? Where they've kind of given me the answer to like a pretty performant way to compare the collision. And this is really a part of building technical intuition, is really just like figuring out, okay, like what are the terms I need to search for, and then going on Google and kind of like doing your own research and reading and understanding. And that's part of the reason why I wanted to record this video today, is because like I don't actually know the answer, like the true answer. Like to know the answer, you'd have to sit down with the engineer on the Apple Maps team, because some of these decisions are so complex that it's impossible for an outsider to really truly understand. But there's like prior work, right? So like looking at OpenStreetMaps, right? You can kind of get a sense of like, okay, this is how the tech used to work, like 10, 15, 20 years ago, right? Where we had these tiles and all these decisions were made on the server side and they're served to your client. And then you're looking at like more modern web tech where like labels are kind of like determine whether or not to render on the application on the client side. And then you kind of look at, like native implementation of that like modern take. And kind of like play around with how does that look? Because for example, like Mapbox, at least on this interface, it doesn't support like spinning around, but I'm pretty sure they do at some point. And it would be interesting too to just compare like, if you look at a specific area, like how does Google handle it differently? Actually, like why don't we do that? Maps.google.com, and let's go to Rodeo Go. Right. So if we zoom in here. Let's clear the search, right? Oops. And so you'll see here that it actually makes a similar decision on what to show, except that Google has much more of like a snappy experience here, right, on the web. Whereas if we look at the mobile experience, it might actually be a little bit more smooth, right? Where we might say, hey, it looks like Google actually determined on mobile that Ferris wheeler is more important, and it's actually bolder, right? And that's actually pretty interesting, right? And if you look at the number of reviews, well, Rodeo Go has more, but I guess Ferris wheeler is rated 4.7. So it's interesting, like Google has made a slightly different decision here than Apple, or even like Google Maps Web. The fact that it's different between these two is actually kind of pretty interesting, and it might be based on like my activity too, because like on the web here I'm not signed in, but on mobile I'm signed in, so Google probably knows some stuff about me as well. In this case, you can see like the Market Center Boulevard label here, like really kind of like colliding with kind of all these labels around it. And this is a case where you'll see that kind of more complex shape collision comparison, right? So in this case, like Market Center Boulevard, right, and Mother's Daughter's Diner is over here, right, and it is in the collision box, but they are doing the further collision to look at the rotated shape. But yeah, like hopefully this was helpful. What are some other things I want to talk about? But yeah, like there are only like best guesses you can make, and that's really kind of the fun. Like in college, I had this class called how stuff works or how it works, and we would basically like get a physical object, like a drill, right? And then our professor would have us just like start playing with it, start observing, taking notes, and then like eventually just take it apart. And then at some point, yeah, you can like go on Google, but like most of the first part is really just like studying this object that you have in your hand as a group and kind of like observing. And to me, this is like a foundation for me of like how I learn and how I can become a better designer and someone who works in technology, is just like sitting down with a piece of technology and being like, okay, like how does it feel? Like what are my guesses? And then like verifying that, right, by looking it up or like asking someone, and then like adding that to my knowledge bank, right, and then doing more and more, right? So it's really about like volume, right? The more things you look at, the better your intuition will be. Yeah, sorry today's video was a little bit rougher, coming off a couple days of side effects from a COVID booster. But yeah, that's the breakdown for today. And if this was interesting, please do send this video to your friends. If you want to, you can like and subscribe. I don't really care, but I care more that you're sharing this with people if it's interesting. And if you do have ideas for things to break down in the future, please do send it to me. Yeah, all of your suggestions are super helpful. And have a good day.